basically a balance of inertia. Inertia and the pressure gradient inertia and gravity at the beginning then becomes viscosity countering the gravitational spread, and then at the end things are driven by surface tension. Okay, so then you have a balance between surface tension and viscosity. So you have three different scaling laws in this. So gravity is always driving it, right, at the beginning. So it's gravity versus inertia. Number two is gravity and viscosity, right? Because Reynolds number goes less than 1. So then you have gravity balancing viscosity, and then surface tension dominates gravity when the thing becomes small enough. And so then you go into a third phase, and so the scalings of radius versus time are different in all of these phases. Okay, and so that's how you can, and you know the variants of this are pouring batter on when you're making pancakes. How does the radius change with time? And so we'll do all these scalings because they're kind of nice. So this is a subject.
Well, the pancake is for the first two phases, right?
Yeah. So this in the first two phases we refer to these as gravity currents. So these are things basically a fluid spreading under the influence of gravity. So the idea is, again, some volume of fluid dumped onto let's just imagine a rigid surface for the time being. So we'll start with the rigid case, then we'll do the oil spill case. But this is a fluid which is dense relative to the ambient. This is rho minus delta rho. And because of this density difference of things spreading, it's going to be resisted principally by inertia if the Reynolds number is high, and by viscosity if the Reynolds number is low. So if we know that basically the pressure is going to increase linearly, so we're going to have high pressure here at the base relative to here. So the thing's going to spread. And we can describe its geometry, its radius, by r as a function of t, and its height by h. Okay, so stage 1, high Reynolds number. So again, just think of dumping a bucket of water onto the ground. And you can define your Reynolds number however you like. U, let's say h over nu, if this is much greater than 1. Then the force balance. So we know that if we look at the vertical and horizontal, so let's just call this characteristic height h. So I'm using r and h to denote characteristic values. I should probably use upper and lower case, but you know what I mean. Okay? So the flow is forced by gravity, resisted by inertia. So we say, if we look at the force balance, we have this radial pressure gradient being resisted by inertia. Okay, and this gives us the characteristic speed of a high Reynolds number gravity current, this G primed H. Okay? So if we know the depth, we can basically say how quickly it's spreading, and G primed here is the reduced gravity. Okay? And you could argue that just on dimensional grounds as well. Okay, but notice that this is going to get slower and slower as h gets smaller and smaller, right? And so eventually you're going to get to the point where the Reynolds number becomes order 1. And at that stage you have the crossover from inertial behavior to viscous behavior.
John, can this h be anything?
Space.
The scale of h?
Yeah, I'm basically saying it's the depth of the. It's the
No,
depth.
no, because it resembles the shallow water speed. So I'm wondering if the h has to be small compared to the length of this blob. Out of curiosity, because it reminds us shallow water speed of water waves.
It kind of is a shallow water situation.
It's like that's a shallow puddle. You know, like the h is small compared to some other curvature or whatever, or it's small curvature maybe.
Yeah. So yeah, I'm not sure that I've made. I'm not sure that we have to make. Oh, sorry. Wait. This should have the same R here at least.
Well, that's all that draws my attention.
Yeah.
It looks like a shallow.
I don't think we've made any assumptions about the geometry. I don't think this is only true in the limit of h over r being very small. I think it's yeah. Okay, and so okay, now the other thing we see that from continuity, again, we'd like to know what r is as a function of time, right? That's our goal in all of these scaling arguments for gravity currents. So continuity tells us that the volume is always constant. So the volume is pi r squared h. Okay, let's just drop the pi, and then we have u is dr dt, looks like square root of g prime to v times 1 over r, because you have square root of h. So r dr okay, so this gives us the desired scaling for the radius on time. T to the 1/2 in the high speed limit. Okay, and so these are actually very robust scaling, so you can do an experiment very easily and get the coefficient. And I would definitely suggest, if you want to solve this problem, let's say you want predictive power over the system, it's far better to do the scaling arguments and experiments in these particular, because experiments are very easy, particularly the viscous one, right? You pour syrup onto a table and you look at it spreading, you're going to see you get a scaling which is very robust, and we can pull the coefficient off without doing any math. Yeah? Okay, and so, but now this is going, we're going to the Reynolds number is going to decrease until we get to the low Reynolds number limit. So this is stage 2. So officially low Reynolds number. And so here you have the flow is being resisted by viscous stresses. So you basically have some shear-like flow in it, which is resisting you now rather than fluid inertia. But again, the flow is driven by gravity, the fact that this thing is denser than this. Okay, so how does the scaling change? So how does R vary with T now in this viscous regime? So this is the pancake problem now. So here we again have dP dz goes as rho g. So characteristic pressure forcing the flow is the hydrostatic. I should do delta rho here. So the characteristic viscous stress now is going to look like U over H squared. And then we can again eliminate H with this. And you get so this is going to be R over T go as rho G primed V cubed over nu R to the 7th. Okay, and so we find in this viscous limit a nice unusual scaling, which is that the radius goes as time to the 1/8 power. And I've done this experiment and it works very well. Okay, so this is pouring, just take a teacup full of honey and you pour it on a table. Well, this is the pancake problem, and you do see this robust scaling, right? And so you can check it out and satisfy yourself and calculate the coefficient. And if you've got the physics right, the coefficient always has to be between 0.1 and 10, right? Unless the gods have conspired against you and thrown in a factor of pi to the 4 or something. And okay, so again, in doing these scaling arguments, you basically get everything apart from the coefficient. So by doing a single experiment, you can deduce the coefficient. And if predictive power over the system is what you want, if you want to be able to predict how quickly something spreads, that's all you need. Okay, so these are generally, by the way, this gravity current, there's a great book on this. If this is something you're interested in, there's a book by John Simpson. I had the distinct pleasure of sharing an office with him in Cambridge. So he was a guy at the age of 65. He retired as a headmaster in England, and he was on the side. He was the British world champion glider pilot. So he got interested in sea breezes. So sea breezes, basically in the morning you get, owing to the temperature difference between the sea and the water, you get these very strong winds. And so this is the glider pilots know about these, and this is what they glide on. And so he was interested in this when he was younger, and so decided at the age of 65 to start a second career as an academic. So he went back and did his PhD. So he did his PhD, and he finished up at 68 or something, and then he got a postdoc at Cambridge. And so the question arose, what did they pay him? What was the salary? And salaries in England at the time were determined by your age. so he said that they agreed that he would be 28 instead of 68 for the sake of the pay scale. But he went on and had a second career, marvelous stuff. He basically developed all of this, did these great experiments, and he really had, contributed more as an academic with a career starting at 65 than most people do in their entire careers. Really a wonderful guy.
Gravity
Yeah, and he's an excellent writer. This is because I actually proofread the second edition of it, and his writing style is fantastic. He's very crisp and very clear. But he has a whole book, and you can imagine. I mean, this is a very important problem. So if there are chemical spills and so forth, how quickly do things spread? And then you can say, what happens if there's a spill underground in the? So if you have some toxic chemical getting into the water table, how quickly does it spread through porous media? And people are still working on these problems, but he really got things going. Okay, so this course is about surface tension, so we're going to now look at the case where things are small. Okay? Okay, so now we imagine we have a substrate and there's a surface, we have to worry about surface tension. Okay. Okay, so we know that there are situations where there are equilibrium between gravity and surface tension, and it's going to want to approach that, but we can also have the flow is going to be affected by both gravity and surface forces. So again, characteristic gravitational pressure is going to be rho g h over r for just scaling. The curvature is going to depend on the detailed shape, but we can say it's going to look like gamma h over r cubed. Okay, so that's going to depend on the detailed shape, but we're going to get that order of magnitude of pressure. So which one dominates? So if we look at the ratio, we get our old friend, the Bond number, coming up. Okay, so that's basically saying when surface tension can no longer be neglected, and when the Bond number becomes order 1. Okay, so the Bond number so this scales as 1 over h. Okay, so that's okay. So if we look at the details, the contact line. So we have gamma solid vapor, it's our liquid phase, gamma solid liquid, gamma we have the spreading parameter. This is an indicator of the extent to which this thing wants to coat the surface, so the difference in the gain in surface energy, or the release of surface energy as the thing moves. Okay, we've seen when S is less than 0, we get partial wetting. Let's just say we have a contact line. Okay, we did this in one of the first few days of class. We saw that there's basically a region here in which there's a balance between hydrostatic and curvature forces, and in here, and basically this will always go to the capillary length, right? So basically the thing will spread until it gets thin enough that this curvature force can balance the hydrostatic pressure across the thing. Right? Okay, so that determines your H. But when S is greater than 0, the thing really wants to coat the fluid. It wants to coat the solid, I should say. And so we can ask the question, how quickly is it going to spread? Okay, so what's the new scaling? We've seen R going as T to the 1/2 and T to the 1/8. How is it going to change when it's surface energy which is causing the spreading? Okay, so we have this force S acting at the contact line, which can't be, we don't have an equilibrium. So we have spreading, forced, okay, so this, and again, what we saw before, the viscous regime, this is representing a third regime where basically now the surface tension is dominating the gravity in terms of driving the spreading. Okay, so you basically say here that the viscous stresses, so mu u over h, so that's the characteristic viscous stress, right? And that's going to act over an area, pi r squared if we're axisymmetric, is being driven, so that's what's resisting the total tensile force, which is going to be S times 2 by R. So this is the tension at contact line, and this is viscous stresses integrated over the bottom of the current. Okay, so this is giving us R dr dt goes as S for mu H S. So let's try and get R as a function of T again. So we use continuity. Again, R squared H is constant. We get R cubed dr dt SV over mu. R goes as SV over mu. It's the 1/4. T to the 1/4. Okay, so we've got a half, an eighth. Now we've got a quarter. But this scaling argument doesn't work. Okay, so this is not consistent with data. So what's gone wrong? Instead, R goes as T to the 1/10. Okay. Do you have a problem with this scaling argument? Looks okay to me.
Well, I think we're considering only one curvature. I don't know if the other one is the
How do you mean?
So, you think in that S, we're only taking account of this curvature?
Well, you're taking into account the fact that there's an unbalanced stress here, right?
Yeah, that's it.
Right. So that's what's driving things. But, so notice that this looks very much like the problem which we just did, which is a moving contact line, right? This thing has basically a moving contact line. And we've seen that, and so we might expect, and we did a calculation for the dissipation in that case, right? And it could be that the dissipation here dominates that, the dissipation here dominates that here, right? And that's what's going to happen, okay? So we've made a bad assumption about the nature. We've assumed that the viscous dissipation happens throughout the layer. In fact, it's localized to the region near the contact line. Okay, so that's going to allow us to get the correct scaling. Okay? So that dodgy bit of scaling which we did in the first half of the lecture will save us. Okay, so let's first look at a little history. So in 1919, a fellow named Hardy. So what does it actually look like here when S is greater than 0? Okay, that's the question. Okay, so we saw that if you actually zoom in at the edge of this current, when S is greater than 0, there's actually a precursor film. Okay, so he placed dust pillars ahead of a spreading drop. And notice that they were knocked down before the drop actually arrived. Okay, so the picture looks like this. You basically have a drop. Then you have this wafer-thin precursor film. So this is, say, a silicon drop. You have this very thin film. And the only reason he could see it is because he put these pillars down. And he found that these would be knocked down by the precursor film. Okay? So how thick is this? So they've now done experiments which indicate that this is around 20 angstrom. Okay, so basically there's this force imbalance at the contact line which acts there, and this locally pulls out this really thin film. Okay?
So this was a way to sort of being able to visualize how far this person was going.
That's right, yeah.
What seems strange about that is that curvature pressures should show that pressure is lower where curvature reverses, right? Right before that.
Here?
Here, yeah.
Yeah, so basically what's happening is this
It's like it's running and
local equilibrium, I mean, basically on an individual molecule sitting there, it really wants to move, and it moves faster than the whole bulk will allow it to, right? And so, basically, we have to abandon our preconceptions of how fluid mechanics works on a molecular scale, which is sort of what's happening.
Contact point.
Yeah, yeah.
And on the other hand, this drawing of yours is a little bit of a caricature or not, in the sense that this precursor film is even bigger than the transition region of the slope. Is that a caricature or not?
No, probably not. Should probably go.
Just a little thing that goes and
Yeah,
you don't have to redraw it, just
yeah. Something like that.
no, I mean how far ahead does it get, right?
Oh, I think it goes, it can go quite far.
Say the transition zone from flat to flat is a given length scale.
Yeah,
Right? This
yeah.
transition zone. And then there's the precursor layer length scale too.
Yeah.
Is it this big, like compared to this transition zone?
It's very small. It's very small. Yeah, so, I mean, yeah, basically everything we know about fluid mechanics will allow us to rationalize this, right? Expect this to be basically capillary length. And then you have this business which you can only see with a microscope.
Yeah, but the length that it spreads ahead,
Yeah.
it's the way you drew it is a caricature or not. I mean, it's exaggerated. But does it really spread ahead that much compared to the transition zone from flat to flat?
Oh,
You see what I'm saying?
yeah, I don't actually know the
Or is it just a
extent of it.
little nose sticking out?
Yeah, no, I think it kind of goes, I think it'll keep going, yeah.
if you saw the naked eye, the knocking down of the pillars, right?
Yeah. Yeah, he did.
So if you saw with the naked eye, it's big.
I mean, one can calculate how quickly this moves. I haven't done that.
It's big, yeah.
Okay, but in any case, so what sets the ultimate length of this? We have to go beyond fluid mechanics to get that. So what sets the thickness is actually van der Waals forces. So it's going to depend on which fluids and which solids you have. Okay, so then we have to revise our physical picture, and this revised physical picture will allow us to get the right scaling law. in particular give us this r going as time to the 1/10. So this is our drop now. We have this wafer thin precursor film. So again, what we actually see in terms of the radius of the drop is r of t. It doesn't include the precursor. And this is basically spherical cap if we're small enough. And so this is our dynamic contact angle if it's moving. And if we zoom in here, we see a slightly different picture than we had imagined, right? We were imagining this spreading parameter being given by this, but it's actually going to be different, right? Because there's actually an additional tension here. So our little zoom box now, we see the following. We see okay, so we now see in the vicinity of the contact angle, contact line, we have theta, so we have gamma pulling in this direction. We have gamma solid liquid, we have gamma solid liquid, and we have gamma acting there as well. Right? So it's quite different from, so the local force acting on the edge of the drop is quite different from this, right? In particular, the force is much less than the spreading parameter because this guy is now acting in that direction, right? We still think of this as a contact line, right? But in fact, because of the precursor film, the force acting on that line is different. Okay? So F okay, so we can again, if theta dynamic contact angle is small. Okay, so again, this is considerably less. So this is much less owing to the precursor. Okay, so now this is yeah. Let's just finish. Let's just get this. Because after this, all of my lectures are easy. I'll get the painful part done in the next 5 minutes. Okay, ready? So, now we just saw the first part of the class. Fu. So now we have to calculate the dissipation in the contact area. So this is defined the spreading speed in terms of the dynamic contact angle. Okay, then we get the following. U equals dr dt equals theta dynamic the Dijon factor okay, and also we're assuming the drop is small, so we're basically putting down a small drop, which is basically a spherical cap. So if we have a spherical cap, then you can convince yourself that the volume is going to be given by r cubed theta. So theta is the angle subtended. So that's basically our dynamic contact angle. So this being the case, we know that the volume is constant. So we can relate dr dt and d theta dt. Now we sub for dr dt from star and we get the following, getting close. 1 over theta d dt equals minus v star now we sub r equals L theta d for minus 1/3, which follows from here. So we're just using continuity again. And so we get the answer is V star (13/3). Here's a non-trivial scaling. Okay, so theta d goes as L over V star T to 3/10. And from this it follows, again from continuity, from this guy, R goes as L V star T over L to 1/10. Okay, so that gives us the T to the 1/10. as we saw previously. And again here, V star equals gamma over mu. Okay, so that's so you can see things get complicated when you're actually looking at contact line dynamics. In particular, you have to get beyond the continuum hypothesis and start worrying about chemistry. It's not my cup of tea. But in any case, there has been a lot of work done. So it's sort of, always interesting the way fields abut on other fields. The people who are interested in these things, a lot of them are surface chemists. A lot of them are, the French physicists, like Degen's group has done a lot of work on this area, and their training is solid state physics. So, but this is sort of at the frontiers of fluid dynamics. So where does the continuum hypothesis break down? This is one frontier of fluid mechanics. Another is how, complex fluids. What happens when things are not Newtonian? You get all sorts of peculiar behavior. But this is one particular, and of course with surface tension, when you're looking at surfaces wetting solids, this is an important question, which so a lot of, again, surface chemists, chemical engineers are interested in these sorts of things. But now we can get back to fluids, having visited the frontiers. So we'll see you on Wednesday. So do you have any more questions on the problem set?
Well, just one question more